In the denominator there is kBT, and in the numerator there are two activation energy terms. One is delta UI. This comes from, this activation barrier comes from diffusion or jumping across the interface. The other one is the thermodynamic activation barrier for the nucleation, and that is delta G star. In some book it is denoted as W also. Now, how is nucleation rate temperature dependent? As temperature dependence of nucleation rate, we have two terms. One is this one, and we said that delta UI, this activation barrier, is not a very much function of temperature. We can assume it's not a function of temperature. Then this I being proportional to exponential minus kT, as temperature going down, this term will be the whole term low. And at T, so this whole term will come down, huh? This term will come down, and at T equal to 0, absolute zero temperature, this will become 0. So your I becomes 0. Now at T equal to TE, what happens? You have also exponential minus 1 over kBT, and what is the W? W is 16 over 3 pi gamma Q delta GB square term. What is delta GB? Delta GB is proportional to 1 by delta T, that is TE minus T square. No, not square. Delta GB is proportional to 1 by delta. Not 1 by delta T. Delta T. That is
delta by T.
Directly proportional.
Yes.
So at T, and so this delta G star is inversely proportional to this T and delta GB square. No, delta G star is just proportional, inversely proportional to this. Yes? So at T equal to TE, your delta GB equal to 0. And delta G star equal to infinity. So at T equal to TE, your I becomes I being proportional to exponential minus delta G star over KT at T equal to TE, your W being infinity, not W, delta G star, your I becomes equal to 0. So I is 0 at T equal to TE, I is 0 at absolute 0 temperature. So as so this is TE, I is 0. Now as you come down the temperature just below TE, what is happening as, so it will go through, so it is 0 at absolute 0 temperature. So it will go through a maximum temperature, like a maximum in the nucleation rate at a particular temperature. Hello. Hello. Are you in a class? Who is this? Class इधर तो लेफ्ट साइड और if I write here, can you guys see? Yes. Your R star is minus 2 gamma over delta GE, and delta GE is your proportional to T minus T. So at high temperature, close to your delta GV is very small. So your delta GV is small, so R star is very large. So delta G star is large, and your NC, that is equilibrium number of critical nuclei, which is given by total number of sites exponential minus delta G star over KT. So NC becomes very small. So very few such large nuclei, because R star, large critical size nuclei, very small number can form at very close to your equilibrium transformation temperature, despite its high mobility. At high temperature, high mobility, but your critical nucleus size at that high temperature, close to equilibrium transformation temperature, is very large, and your activation barrier corresponding is very large. So number of such stable nuclei that can form is very, very small. Your nucleation rate is multiplication of two factors. One is this number, equilibrium number of stable nuclei, multiplied by the frequency factor. So even though the frequency factor is very high, but NC is very low at high temperature. Now as temperature comes down, your R star comes down. As temperature comes down from this, so at this temperatures very close to your equilibrium transformation temperature, your NC is low. NC is very small. Even though around these temperatures, even though high mobility, so mobility is high here. But as you are going down the temperature this side from your equilibrium transformation temperature, what is happening? Your R star comes down very rapidly. So at R star comes down rapidly, more rapidly than your mobility comes down. As the temperature is lower, your mobility comes down, R star comes down, but at initial stage R star comes down much faster. So NC becomes, NC number of such particles 7 pi becomes very high. So NC going up is faster at initial. So even though mobility comes down, but still NC is very high, so your nucleation rate increases. And after that maximum temperature, even when you go even further, your mobility comes down so much that your jumping process frequency of a critical size embryo to become a stable nuclei, that comes down. So your nucleation rate comes down. So even though R star is coming down here, but mobility coming down is much higher at this position. Here R star coming down is much higher compared to mobility coming down. Now the question is this temperature at which your nucleation rate is highest, that Tm, how to find out Tm? There is a graphical method, so where it says that if you know the delta G star as a function of temperature, so say it is known, say if it is known, then you can plot that where delta G star will be in the y-axis and your temperature is this axis, and at t equal to Te, your delta G star is infinity. So it will go something like this. Whatever the form, if you know the delta G star variation with temperature, if you can plot it, it will go asymptotically towards infinity at T equal to T. At low temperature it will be 0. Say at T equal to 0 it will be 0, and till certain temperature it is very, very small. So if you know this and you know your equation of nucleation rate, which is given by this equation, I equal to A exponential minus delta Qy plus delta G star over Kt. You take logarithmic of this, ln I equal to ln A minus delta Uy over Kt minus delta G star over KT. The derivative of this ln with respect to temperature. This is a constant term, so it will be 0 minus, and delta Ui we are taking it as not a function of temperature, whereas delta G star is a function of temperature. So this will be minus delta Ui over Kb.
It is correct.
And t to the power minus 1, so minus t to the power minus 2 square.
This will plus.
This will be plus delta G star over kbt square. Will there be any other term? 1 over kbt yes, at t equal to tm, at t equal to tm, your I is maximum. That means ln I is maximum. So del ln I del t will be 0 at t equal to tm. At t equal to tm, this term becomes 0. So 0 equal to ui over kb tm square plus delta G star kb tm square minus 1 over kb tm del t of delta G star at t equal to tm. From here we can write your delta G star delta t at t equal to tm is equal to with which, from this we can write this delta G star delta t at t equal to tm equal to ui plus delta G star over kb cancel delta ui plus delta G star by tm. So this equation, if you note, what is delta G star delta t? It is the slope of this curve. This is a slope of this, the left hand side is slope of this curve at t equal to tm, which we do not know yet. So at some point on this and at some point on this curve, that slope is the left hand side. Right hand side is delta G star plus delta ui over tm. So delta G star is from 0 to some value delta G star. So what you do, you first, if you know delta ui, you take that point from 0 to in the negative direction, the delta ui point. From here, you draw a tangent to this curve, okay? your first step is you draw a point from 0 in the negative side, delta ui, you draw a tangent from that point on this curve. Wherever it touches, this point will be your Tm according to that equation. So this is your delta G star, this is your delta Y, and this is your Tm. So this divided by this length is your slope.
So how do we draw this line? TM is not known, right?
Which was?
TM is we are finding TM.